During this session I'm going to be talking about refraction. This is the process where light bends a boundary between two different mediums. So let's start off with, I guess, a thought experiment. Well, it might not be if any of you are fish spear hunters. Or, if you're not a fish spear hunter, if you've ever noticed how it appears that fish swimming in a river seem to be very, very close to the surface. Now, the reason for that is because of this process known as refraction. So if you think about it a little bit more carefully, imagine what you're actually seeing when you look at a fish inside the water. Here's an example of, I guess, one of the ultimate fish hunters, a heron. And what they do is a heron's an ultimate fish hunter because it compensates for refraction. It does the calculations you're going to learn during this session, automatically and instinctively in its head. Now, what happens with these fish is that what they actually see, or what they perceive to see, are two different things. Or I guess where the actual location of the fish and what's perceived to be is different. The mind always thinks that light travels in straight lines. So that means that even though the light travels from the fish, is bent, is refracted, it goes from the water into the air, what the fish sees and what the fish perceives is that light travels in a straight line. So the image of the fish is actually much closer to the surface than it really is. Now, due to the experience of the heron, they've worked out that if they strike just ahead of the fish and a little deeper, then that's where the actual location is, and that's why they're so successful at catching fish, because they've automatically understood the laws of refraction, and that's what I'm going to try and train you to do during this session. So, how refraction works. What I'm going to do here is I'm going to turn on my imaginary ray box. So here I have a ray of light, and what's happening is the ray of light is travelling from air into glass, and as we can see, what takes place is a bending of the light, and it occurs at every single angle except we're running straight along the normal, and the light doesn't bend. But at every other point we see that light bends, and the amount of bending of the light is what we're going to think about when we're thinking about refraction in a little bit more detail. Okay. So that's the general idea, it's the bending of light, and we're going to try and link together the ideas or the angles involved in this so you can make some calculations of your own. First of all though, there's a reason for this bending, and the key reason behind this bending is the fact that although we accept the speed of light as to be 3 times 10 to the 8 meters per second, it's often missed that this is only in a vacuum. When it's not travelling in a vacuum, the speed of light is dependent on the medium, and that change of speed is the key reason behind this bending as it changes from one medium to another. As it happens, every medium has something called a refractive index. Now, the refractive index of a medium is actually a value which has no units. It's a ratio of the speed of light divided by the velocity of light in that medium. Now, what happens here is this value is always going to be, as we've got no medium where the speed of light is greater than the speed of light in a vacuum, the number that comes out is going to be from 1 upwards. And the slower that the light travels in the medium, the larger the refractive index of this medium. Let's think of this in a little bit more detail. A question comes up. What is the velocity of light in benzene? Okay, so what we can do is we can look up a few things. First of all, the given information is the refractive index of benzene is 1.5. And the speed of light, as we mentioned beforehand, in a vacuum is 3 times 10 to the 8 meters per second. The unknown in this question is velocity. Using the equation, the refractive index equals the speed of light divided by the velocity in the medium, we can rearrange and then substitute, and that tells me the speed of light in benzene is 2 times 10 to the 8 meters per second. So that's the idea of that the speed of light is different in different mediums. So let's go back to the idea of refraction now. I'm going to join that idea up later on in this discussion. So if we think about light striking a glass block, bending, and as the light ray continues, as it leaves the glass block and goes into air, again there's some bending. What I've shown on this diagram is I've shown the normal, which is obviously an imaginary line at 90 degrees to the surface of the medium. We've also got a situation here showing that when light is travelling along the normal, there's no refraction whatsoever. So in both of these situations, I need you to now try and imagine what's going to happen here. The outcomes are written here. As the wave slows down, it bends towards the normal due to entering a more dense medium, and the wave speeds up and bends away from the normal due to entering a less dense medium. As I mentioned before, wave slows down but is not bent due to entering the medium travelling along the normal. Now the idea of this, I think some of the best ways to think of it, rather than thinking about a ray of light, imagine a wave front. What happens is that one part of the wave front reaches the new medium first, and that causes it to slow down. That slowing down means that the other end of this wave front carries on travelling at a faster speed, and it kind of overtakes itself a little bit, and that causes the bending. So here's some terminology which we're going to use. First of all, we have the incident ray. That's the ray which is approaching the boundary, and then we have the refracted ray. That's the term for the ray of light after it's gone undergone refraction. The angle between the incident ray and the normal is known as the angle of incidence, and the angle between the refracted ray and the normal is known as the angle of refraction. So these are the key terms we're going to be using. And we're talking about here medium 1 and medium 2. So there's a change of mediums. So those are the terms we're going to use. All this comes down from Snell's law. So what happened is a guy called Willibrod Snellius discovered that for any two media there was a relationship. The relationship showed that sine theta 1, that's the angle of incidence, divided by sine theta 2, that's the angle of refraction, equals a constant. As it happened, it was also discovered that the velocity of light in the first medium divided by the velocity of light in the second medium is also equal to the same constant. This constant, for now, we're going to recognise as 1 and 2, showing that we're going from medium 1 into medium 2. So it's a boundary condition dependent on the two mediums. Putting these things together, we find out that the refractive, what would be the refractive index of this boundary, going from 1 to 2, is sine theta 1, which is the angle of incidence, divided by sine of the angle of refraction, equals V1 divided by V2. Now if we combine this bit of thinking here, since we already know that the refractive index of a medium equals the speed of light in a vacuum divided by the velocity of light in that medium. That means what I can do is, from this other factor, if I combine these two features and recognise that the refractive, or 1n2, is actually, can be better shown as n2 divided by n1. So two separate refractive indexes. The refractive index of the second medium divided by the refractive index of the first medium. All this comes together to show what is known as Snell's law. n1 sine theta 1, so that's the first medium, and divided by the sine of the angle of incidence, equals n2, the refractive index of the second medium, multiplied by the sine of the refracted, or the angle of refraction. So this is the law you're going to use to do any calculations. And actually it's quite useful, because what happens in many situations is when we're looking at a second medium, we normally assume that n1 is that of a value of 1 because we're assuming that light's coming through a vacuum. So that's the law you're going to have to use to effectively think about with a refractive index.